welcome to, for the students in the room, your final Data Science Speaker Series lecture of the year. So another little point of completion for you. Congratulations. To our visitors and guests, thank you very much for coming. These speakers are sponsored by the Data Institute, which is the umbrella organization for all data science and data engineering programming and research that happens here at the University of San Francisco. Thank you so much for joining us. We are thrilled to close out this academic year's series with our guest, Dr. Srini V Srinivasan, founder and CTO of Aerospike, and a leading voice in real-time data systems. As AI continues to advance, the need for lightning-fast, context-aware decision-making has never been more critical. Whether for fraud detection, intelligent automation, or delivering hyper-personalized experiences at scale. Today, Dr. Srinivasan will walk us through the technical challenges and innovations that make these systems possible, drawing on more than 2 decades of experience building real-time infrastructure at scale. Please, everyone, join me in welcoming Dr. Srinivasan.
Can you hear me? Can you hear me? Okay. Yeah. There's a little lag between the time I turn it on. Yes. So, thank you, Elizabeth, for a warm welcome. And it's a pleasure for me to be here to talk to people who are interested in data science and data in general. My background, my Ph.D. was in database technology from the University of Wisconsin a long time ago. Data in those days was not as pervasive as it is today in our lives. It was mostly restricted to a lot of enterprise-related things. And so I worked on, early systems in databases for a while, after which I guess the internet happened. And I switched over from my expertise in databases and so on to become somebody who built applications using data for almost 15 years. And at that point, I was at Yahoo, and we discovered, and we were working on mobile technology. We discovered that for a lot of real-time mobile applications, the traditional databases that I was very familiar with and I was still using, this was in early 2000s, maybe after 2005, 2006, just before the iPhone came out. And what we discovered was the existing databases didn't really work when they were needed to access applications at scale in terms of all the consumers and so on. So that's what started this journey. About 15 years ago, I co-founded Aerospike with other colleagues, who was an expert in networking, and I brought my database and distributed file systems expertise to it. So what I'm going to take you to today is essentially a way to look at real-time data access, which is used for decisioning as well as hyper-personalization. This is, I talk about consumers and how we were struggling in the early 2000s to satisfy mobile requests with existing databases. A lot of new databases were invented. And today, in the context of this, I will take you through a few use cases so you kind of understand the challenges that we try to solve. And of course, now we have solved it significantly. It's been 15 years of solving these kinds of problems. And the truth is, every one of you is using some of these techniques and as you go about your daily life, using your phone and using the internet and so on. If any of you wants to stop me, some of this talk can be really technical. I will try to stay at a high level as much as possible. If you have questions, feel free to interrupt. And then hopefully I'll also have some time for questions at the end. So there are a lot of mission. So when I'm talking of use cases for these kinds of systems, I just want you to understand the general area in which we're working. We're working, I put some customer names here, but it's less important. Look at things like recommendation engines. When you go on a shopping site like Wayfair, when anybody goes on that, and there are recommendations will show up. And there's a practical things that the system has to do in a short amount of time. In all of these applications, there is a real-time SLA. Somebody comes on the website within like a few hundred milliseconds, you have to throw up a recommendation when they're looking at things so they can actually change their buying behavior based on the recommendations provided is properly relevant. So you can't just throw anything there. You have to throw something which is relevant to that particular person as much as possible so that you have a better chance that you will get somebody to be interested in it. And that means there's a short time to make a decision, and the decision has to be data-based and behavior-based. It's all data, basically. And the decision has to happen in a short amount of time, and you have to make the best possible decision. So if you look at more data, you can make better decisions. So how can you do all of that in a short amount of time? Every one of these use cases is like that. Okay, so recommendation engines is like fraud prevention is the same thing. A transaction is in process, and that before the transaction completes and the money is transferred in this case, if it's a payment transaction, you need to have a fraud score for it. So the fraud score is low, which means it's not fraud, then you can let it through. Otherwise, you basically, in fact, if you don't get the fraud score in time, you still let it through. Because you can't just block like 20% of the transactions if you don't have a fraud score. So it's important to be able to get that fraud score in a short amount of time as the transaction is in progress. So that's kind of the general gist of everything here. And then there are various other use cases here I won't go into. Because I just want you to get a gist of the kind of use cases. I'm going to take 3 specific cases and then go over the system and see how the system actually helped with those few cases. Okay? So hopefully it's a little bit of a tutorial. The most interesting thing here in all these use cases is the SLA that I talked about, as well as the scale. Here's a fraud prevention use case, which is based on reducing false positives. Right? You want to get a properly validated fraud score. There's a lot of detailing here, but look at the requirements in the bottom part of it. Okay, one of the important thing is you have a system which works at scale. In this particular case, this was actually from 2015, almost 10 years ago. They might have a lot more customers now. There are 150 million consumers, and there are lots of database operations per transaction to compute the fraud score. It has to happen within about 200 milliseconds. And what they were looking for is a way to reduce the OPEX and CAPEX. Okay, and I'll talk about it because when you have to do things in a fast amount of time, in a very short amount of time, you need to have the data in very fast storage. The fastest you can typically store is in DRAM. Okay, but DRAM gets expensive. And you also have flash, and that's kind of innovation that Aerospike, I'll go into it in a bit. But that's one way to reduce the operational expenses and the capex is by using storage technologies in this case, which are equally fast, but which are maybe 10x lower in terms of price per bit. And the return on investment is important. They wanted to continue to improve the load. In all of these use cases I'm going to talk about, the problem that we're trying to solve, similar to the one I encountered at Yahoo before we started this company, it's all about scale. The first customer needs to have the same user experience as the 100 millionth customer. If you don't do that, you don't succeed. And that's kind of the whole thing. So there's a whole idea of how to do fraud in a short amount of time. This is one use case. Another one is a digital identity system. ThreatMetrics is a company where they analyze user behavior in general, and they offer their services to institutions like financial institutions like banks and so on. So when many of you go and log into your bank's website, it is highly likely that there is an extra call that goes out to ThreatMetrics from the bank's website asking ThreatMetrics, it may even ask multiple services. One of them will be ThreatMetrics, which is actually part of LexisNexis right now. And then they will ask it, hey, this person is on the website, they're logging in from, like, right now I'm in San Francisco, or, based on, on the connection, it could be, my phone will tell them that, or if I'm going to be in Europe, like I'm going to be there tomorrow, So it will know all that. And then it will basically go back and Metrics has a bunch of information using third-party data and so on. And they'll be able to provide a level of confidence that this is in fact Srini who's logging in to the bank. And that fundamentally has to happen in a short amount of time, because if you don't do that within 50 to 100 milliseconds, there is no point in having a service like that. A third one is more like trading and risk. I can't talk about the company here, but I can say that I saw their office when I was traveling today. So the important thing is here, this is a system, this is a brokerage firm, and typically they have the ability to evaluate risk on these various accounts that they have. And this has to also happen in a very short amount of time. Before using something like Aerospike, they were doing it overnight, but that is not enough given the way the stock market changes during the trading period. It is not possible to actually run a good, efficient margin loan system, for example, business, if you didn't know what is going on in the market and the account and everything. So if you would be able to run the risk calculations every few minutes instead of overnight, you have a better way to automate all these things. And with AI and everything happening right now, this becomes even more important. So that's kind of the other aspect to it, right? In this case, the way you can apply AI to it is to optimize the recommendations for portfolio trades based on latest market conditions and so on. And that's really, really important. Okay. I'll talk a little bit about the general system in the context of Aerospike that is actually delivering some of these applications, the database support it needs, that the applications need in order to deliver whatever they need to do to their customers. Typically, as I pointed out, these are applications which look at a bunch of data and then come up with a decision using various AI/ML algorithms and so on. And that's really the general pattern of this entire system. So what I have here, I won't go into the, if you have questions, feel free to stop me, but I just want to point out some base structure, okay? First of all, this is a product, it's a database product, which has a bunch of ecosystems around it, okay? The central box there talks about a high-performance storage engine. I'll go into it a little bit. So that's one block. And then on top of it is real-time data processing. There is a whole thing about distributed systems. So one of the things about consumer-grade decision-making apps, like what I'm talking about here, is they have to be fast. They have to handle, which means low latency. They have to handle a lot of requests, which means high throughput. But they also have to stay highly available, which means they have to be 24/7 available. Because if you don't have any of these capabilities, you will not be able to run a large business addressing millions and tens of millions and hundreds of millions of customers. Okay? And that's kind of the fundamental basis of this. So which means real-time processing, having a distributed system which can work together in terms of delivering these kinds of low latency, high throughput, and high availability is something which is really important. There's a whole bunch of algorithms on the real-time data services. And then the more interesting thing for database developers is the kinds of data types and data models that these systems can support. And in this particular case, it is we support key value, document, graph, and vector data systems. So vector is more related to the AI-based searches. Graph can also be used for some of those. But there's a whole bunch of work that we've done in these areas. And then any database system, and then this runs anywhere, typically on any of the cloud. And then there are various client-specific things you can do, like you can write an application in C or in Java or Go or Rust, pick your favorite language, and you can then communicate with the database. And it also interoperates with systems outside, like Spark, Trino, as well as streaming systems like Kafka and so on. Okay, so that's kind of the general overview of the product. And then a graph service is typically something we can build on top of the product. So on the right side of this, right, is essentially the product I showed you in the previous slide. It's the Aerospike database is sitting there. But on top of which, Thinkerpop is actually an open source graph, I would say, data model component, it works with Gremlin as a query language. So there are things that you can build on top of the data layer using Tinkerpop and Gremlin. So you can now program your graph applications in Gremlin and Tinkerpop, and then underneath the covers, there will be the Aerospike system. So what you get out of this is a more scalable graph. So if you have graphs, again, go back to the consumer scale. If you have large amounts of graphs, then you can't usually run it on one node. You're running on a distributed system, and that's kind of what happens in this case. Okay. And then the last point about the product that we talk about is the vector search. Vector search is typically using a similar model to what I showed in graph. There is a data layer, and then then you have essentially the ability to build a vector index and then search it. Vector indexes, I won't go into the details of it. If anybody's interested, we can talk about it later. But the point is, they can also be split across multiple nodes. And there are models like HNSW, which is the one that we use. Essentially, it stands for hierarchical navigable small worlds. That's what HNSW means. And the way the index works is you can search at the various layers of index. You can search at the top level, and then you can then dive deep into the next level, and you get more nodes, and then dive deep and you get even more nodes. So essentially, think of it as a way to find, like you have an image, and you have image of a cat, and then another image of a cat, or a whole database full of cats and other images. You can just look at the vector that you generate out of the image of a cat, and you can match it with anything similar. And you can do that really fast using the indexes that I'm talking about. But in order to do that across a large set of data is hard. That's the other thing. Okay, anything can work really well if you're looking at small amounts of data. When you have large amounts of data, and it's typically consumer scale, in terms of number of people, number of devices, number of activities that are happening worldwide, then you get into real serious problems. And there are lots and lots of applications which require that. Yes, please.
On the previous slide, what does it mean for the interactivity software?
The important thing about self-healing is the uptime. So when you mean the self-healing, what I mean is when a node typically fails. The question was about what does self-healing mean in this context. It just means that the system is able to have replicated data, and it's able to continue to process queries even if a node fails. That is it. And sometimes even a whole data center may fail if you have multiple data center system. I'll talk about it a little bit. But those are the basic. It really leads to uptime. Okay. So the three concepts I want to talk about in terms of what are critical in order to build a system which satisfies these requirements. The first is horizontal scaling. This just means that you have building blocks that you can add to the system one by one, and that will end up in having a distributed system which will deliver for you a unified look at the various data that you have in the system. So the application doesn't have to worry about the distribution. And this system will stay up. That's kind of fundamentally the whole concept here. And there are a whole bunch of technical details here, but I just point out the benefits quickly. Any distributed system has to avoid hotspots. So the question on self-healing, that's really important, because if you can create a hotspot when a node goes down, then your system will go down. So you can have cascading failures. And one piece of the system goes down, another one goes down, another one goes down, and basically the whole service is gone. So you have to avoid any hotspots from forming in the system. It's a fairly technical thing, and that you solve that using parallelism, by using replication, which means you have multiple copies of data. You can access them in parallel, so not a single device or a single processor or a single storage unit doesn't become a bottleneck. Okay? And that's really fundamentally important. In the one thing about the work we did we've been doing at Aerospike, which is unique, is that we also have a smart client. We have a cluster of nodes, which is what I've shown there in the yellow boxes there. There are a bunch of servers. You just in Aerospike, you can just add a server, and then it'll have additional capacity. It'll just merge itself to the entire cluster, and then it'll just continue. To some extent, that is the self-healing part. It's not even healing; it's just like self-managing, so to speak, in that case. So that is kind of limited. But also the clients, which are shown in the blue box to the top, essentially have a lot of pieces of data. One of them is the ability to know where data is in the cluster. So this is why they're called smart clients, or they have the intelligence to detect it. So which means any access to data in Aerospike can be done in one hop from the application. It's typically embedded in the same, the client is embedded in the application. That's why we write the clients in various languages. So you end up having the ability to directly go to a data item. And that's really important. So we can do linear scaling across. It's a shared learning architecture. That's kind of a detail. I'm from the University of Wisconsin, where we invented that. So clearly there's an impact on that. Dynamic cluster management, similar to the self-healing discussion, it's got auto failover, rebalancing, rack awareness, which means that you can isolate failures to racks, which is a pretty common thing in data centers. And we also leverage it in the database. And then there is prioritization, okay, in terms of real time. And see, that's the hard point. The point is, like, when you're running transactions on a system, you're looking at a user data. Let's say somebody comes in and checks my account. Okay, so I'm checking something, and the system goes and accesses my account. At the same time, a node has failed. Okay, now a lot of data needs to move around in the cluster just to rebalance the system again. Now, if that activity is happening, while many people like me are actually accessing the system, how do you make sure both of them happen so that I'm able to get my data while this underlying movement of data also happens without bringing down the entire system? And that's what the real-time prioritization needs to be. It needs to manage these things very carefully so that your system can continue to run and people will not see any of the effects of some of these activities that are going on in the background. Okay. Then we also do active-active replication. I'll talk a little bit about that, not a lot. Now, this goes deep into the algorithms a little bit, but let me make it simple by saying, so everybody must be familiar with what hashing is, right? Okay. So essentially what we do is we use a particularly special hash function called the RIPE-MD 160. We didn't invent it. It is a cryptographic hash, but it has got very good characteristics in terms of collision and so on. So you could take any key that you know of and you can hash it. It will not duplicate the digest. The digest is 20 bytes. That's the 160. 160 is 160 bits. So once you have that digest, which is pretty much for all practical purposes unique, maybe quantum computing can come and break it. But until then, I think it's going to be unique. But the point is, then we take 12 bits of the hash and we partition it into 4096 partitions. So the key space is partitioned into 4096 partitions. The interesting thing there is, because of the RIPE-MD 160 hash, you will guarantee uniform distribution of data in your partition. Okay, and that's kind of just happens due to the math. And that's kind of the important thing there. And then we map the partitions to nodes. And that's the table that's shown there. There are 4096 partitions, and there are like 5 nodes, in this case A, B, C, D, there are 4 nodes. We are mapping those partitions to nodes. And this is basically the fundamental distributed partitioning algorithm that we use here. Okay? And here I'm showing you what happens, when a node goes in and out of the cluster. Okay? So one node has died, and then what has happened is you see the whole partition thing has shifted to the left. And now the node has come back up, so it's now shifting to the right. Okay? You just failed A. When A is failing, this is kind of how the partition map works. And you can see how it shifts to the right and the left based on whether the node is in or the node is out. And it's really important that this actually, there are some choices you can make in terms of how to design the partition map. So do you want to make it so that the data movement is minimal and not go in and out of the cluster? Or do you want to minimize skew in the system? But I won't go into that. But the point is, there's a whole bunch of detail in there in terms of algorithms. The most unique thing about our system is what I've shown here. Typically, there's one thing you take away from this talk. This would be it. What we have done in Aerospike is we've invented an algorithm where we can make real-time data sit in flash storage. Okay. Typically, when you want to get sub-millisecond read-write response times, you have to store the data in DRAM. But what we did in Aerospike is, because of the characteristics of SSDs, where you can do direct random access, we rewrote the entire database's storage system. We built our own storage on top of flash, and then we split it into what we call the hybrid memory architecture, which is the index for these objects is fully resident in DRAM. So you have an entry in always in memory for any object in the database. So there's exactly one request to persistent storage, in this case SSDs, which can be random access. And now not only can it be one request, which means we can bound the latency, it can happen in parallel. Because it happens in parallel, you can actually push a lot of throughput to a single node with multiple SSDs in it. And that fundamentally means we don't have, what is shown on the right is a typical database system which has buffer pool based access, which means anything in persistent storage has to be brought to memory and managed in a buffer pool, and then you have to read it. That works really well if you have what is called a working set. A working set is you read something and then you work on that item for like a while. Then you can afford the first hit for a low or a high access time for the first access. Then if you're looking at it 1,000 more times, it's in memory. But that doesn't work in all the applications that we talked about today, the consumer coming in, to Wayfair and going away, you don't get that working set effect. People just come in, they buy, they go, and they may not come in for a long time. So there's no point in caching it for 5 minutes because the person has come, bought, gone. That's it. They're going to come in 2 weeks, or the item didn't show up, and they'll come back and say, "Hey, what happened? I ordered it, didn't come." But so those don't work. So that's why this particular thing makes it highly parallel, and I'll show you the real benefits in terms of TCO when we do that. Now, it's all well and good that now I can store a lot more real-time data per node. Instead of storing, let's say, half a terabyte of real-time data, if I put all the data in DRAM, I can now store 50 to 100 terabytes of real-time data per node. Great. But what about transactions? If you're running 1 million transactions per second on 10 nodes, now I'm running it on 2 nodes, I'm going to run like 5 times the number of transactions per node. So we also had to spend a lot of time working on how to optimize the CPU and network performance. We work with Intel, we work with Amazon, we work with Google, we work with a lot of people, who are producing infrastructure. Even we ourselves are infrastructure, database itself. But underneath us is a lot of infrastructure on the cloud, in processors, storage, and so on, right? I talked about storage and how we optimize that by basically reducing server sprawl and reducing large clusters to small clusters. Because if we can store 50 terabytes of real-time data per node as opposed to 1 terabyte, I've reduced the sprawl by almost 25 to 50 times, right? And that's hugely important. So you're having a 1,000-node cluster, you have a 50-node cluster now, which makes it a lot more different. Now you can actually handle the entire world's mobile traffic without actually running through problems, right? So that's what this gives you. So it gives even startups the ability to build things at scale without having to spend the kind of money that Google and Amazon spend on it. Okay? That is, if you look at it from the business point of view, that's the advantage Aerospike brings to the table. We basically have technology which anybody can use from the beginning and grow it up to all the way up to Google scale. We've had many customers who've done it over the last 20 years. Okay, and they've got IPO and everything, all using Aerospike. I'm not saying they became big because they use Aerospike, but we were a key component to it has to be the right kind of use case, right, for which we can help you. And here, for example, we can do 15 million. We demonstrated this several years ago, doing 15 million transactions per second on a single node with some technology that Intel built on the network. Without it, we were getting 8.6, so almost double. And this means now the fact that I compressed all this data into smaller nodes, this will help you run more transactions per second through those nodes, so you're actually in good shape. And so everything is more predictable, everything works better, uptime is better, everything actually gets better. This is the main reason we exist as a company. The product used in this. We're also a database, which means we have to deal with safety of data. The most interesting thing about and think of us as in data science, a lot of analytics and OLAP databases are used. We are an OLTP database, transaction processing database, but we work on what is called predictive analytics. These are the things where you have to make a decision whether something is a fraud or not. Something is is a recommendation system, what recommendations you have to make. So the predictive analytics means you have to do certain analysis, but you can't do the kinds of analytics you do in the back end, because that'll take a while. But you need to still make a very good decision, right? And this happens all the time in AI because you have all these models you generate, but then applying the models to some specific data means that you take all the knowledge that you have generated in your long-term models, but then you apply them at runtime. Okay? So that's kind of what's happening. But then a database also has to keep the data safe, which means these are pretty much standard database concepts from a textbook, pretty much. Strict serializability, linearizability, and sequential consistency. I mean, all this means is when you're running strict serializability means that when you're operating on a set of data items, then there are other transactions operating on other sets of data items. Some of them may basically coincide. You isolate it, which means it's atomic. And it is as if all the transactions happen one after another. The system will actually manage it, okay, for you. So you don't have to ever worry about doing something in the database, getting an answer back, and ever worrying somehow that answer is not correct anymore. Somebody else came in and changed it. Never going to happen. And those are the kinds of things and there are various things that we have to do, and we've done all of that over the years. One of the things about this is again a little bit at the low level, but this is an important one. Aerospike does what is called synchronous replication, and we don't do quorum-based. If you're familiar with quorum-based replication protocols, like Cassandra, if you're familiar with that, uses quorum-based replication protocols. If the only reason we're able to get away with synchronous replication when you do a write, the write goes to every replica in Aerospike, is because of all the other things I talked about earlier, which is the system is really fast. We work on optimizing the in-memory pieces, the storage pieces, so which means we can actually get away with doing synchronous replication. And this gives us a lot of interesting benefits. Here is one benefit which you get. Now there are systems which are deployed on our product, on our infrastructure, which actually run 24/7, and they are used for transferring money. Okay, the European Central Bank has implemented an interbank money transfer application for individuals in Europe. They did it in 2018. And how they do it is they run it on. Okay, so this one, unfortunately, I think that I gave this talk in India last. I didn't change the cities. Just imagine one is San Francisco, Dallas, and the other one is, New York, right? So what happens there is you can shut down the New York data center, and the main thing I want to say is the system will continue with full correctness as well as full availability on the other two data centers. Okay, so that's really fundamentally important to understand, and we can actually have systems like that. Everything that is fast. I talk about speed and synchronous replication and so on. We can make it work in a distributed system also, and that's really important to understand. We also have the other side of it, which is asynchronous replication protocols. Okay? So if you are running a cluster in New York and a cluster in San Francisco, in the previous system, I had split the cluster across those San Francisco and New York. Then if you do a write, I talked about synchronous replication. A write on a cluster, which is actually stretching across the entire continental US, will take 100 to 200 milliseconds because of the speed of light and the network issues. Whereas if you can afford that you can afford that for a money transfer transaction because you need to get the text within half a second. I think I transfer $10 to one of you. It just half a second is more than enough to get this. But on the other hand, there are things that happen like a real-time bidding loop in an ad tech system. So you are on a website, and then, every time any of you go on a website or on an app, there is a whole real-time bidding happening. So based on who you are, in terms of your behavior, there are people bidding against your particular um, profile, if you will, so that the people are bidding are the ad advertisers. And then there is a broker in the middle who basically picks the right ad at the right time. So the context is everything. Because if you actually putting the ad in front of somebody and they never click on it, that's a complete waste. And then if you're putting, and then this whole bidding loop means how much is an advertiser willing to pay for a certain kind of user, so the ad can go in front, right? All of this has to happen in 50 milliseconds. You can't afford to stretch that cluster across New York and San Francisco. It's not going to happen. So then you use these kinds of techniques. So you run multiple clusters and you do asynchronous applications. So if I am now here, then in San Francisco, then my data is here. Let's say I take a flight and show up in New York or somewhere in Europe, then that can show up so the first time it will be a little slow, but the data will be there. So now everything can be manipulated in that data set. Because what happens is, because it takes like several hours to get from here to any other place, which is geographically different. What happens then is data will already be there by the time I reach them. And then I can start using it there. And then that'll come back here by the time I come back, right? So you now have what is called asynchronous replication. You just do it locally. Wherever you are, your data is there, and then you move somewhere, by then the data has been replicated, and you go there, and then you use it there, and then you come back, right? So this one actually works really well, because then you don't have a hit. Everything goes really fast. And so real-time bidding loops work really well for any user's data, anywhere in the world, at any point in time. And that's asynchronous replication. You can see the various complex topologies, right? You can just link these clusters together in various ways, depending on what is required. So what are the benefits of this? Okay, to give you an idea, a petabyte scale database in OLTP is fairly large. Analytics is probably par for the course. Okay, so we're talking about OLTP here, and in just 20 machines, this was done a few years ago on this is an Amazon, but it also works on Google, Google instances, Z3 instances. So what you have is 20 machines. We're able to run essentially a database of a petabyte scale, which is kind of compressed in this case. It's really 250 terabytes. It's compressed 1 to 4. So 250 terabytes of unique data, 2 copies, which means 500 terabytes of real data in the system, plus almost half a trillion unique keys. Okay, all of this running on 20 nodes with millions of reads and 70,000 writes a second. But the interesting thing here is not that we can do it. We can do it with a latency of less than 1 millisecond. This is all sitting in SSD. We're still able to do, data sitting in SSD. We're able to do less than 1 millisecond. And then the writes themselves are 99% under 1 millisecond. And this is actually driving a lot of the consumer apps. Okay, that's what. So it now becomes affordable for anybody. One of you wants to start a company, and this just takes off. This kind of stuff is helpful because you don't actually have to invest a lot of resources to make this happen. And it cuts the database costs by a lot, basically. With respect to other systems. Again, the comparison here is not between our system and that is other specific system that is shown there. It's really between storing the data in SSDs, like I said, while storing it all in pure memory. And in order to do that, you have to do all the other things I talked about in terms of the transactions and make sure that you can handle more transactions per second per node. There's a lot of technology we have to build to reap the benefits of storing the data on SSD. Okay, here is actually a little bit more detail on the fight against e-commerce fraud. This is from PayPal. As you can see, right, there is a lot. So what PayPal did was they put the Aerospike in the middle. So what is everything I'm talking about is, can a fast database system help in solving these problems, right? That's kind of the whole point here. And this was the first use case I talked about. This is how actually they ended up doing it. They put Aerospike in the center, and then they actually use other systems too. It's not like Aerospike is the only one, but we are like the center of the what I would call the real-time aspects of things, because that's what makes this whole thing work. And then they implemented a graph system using the Aerospike key value store. So even though Aerospike I showed earlier had a graph API, they didn't use that because this was well before. It was 10 years ago. We didn't have anything. In fact, this gave us an idea that we should build a graph API on top of Aerospike. And what they have done is they have creatively used Aerospike to store data in it, but also retrieve data as and when a request, you see the risk decision service, it actually queries it in real time when the transaction is in process and makes a decision. Okay, and this is how these things get set up. And everything on top of that is basically online. And offline, they're using other more traditional analytics-based systems to solve it. Okay? Because they need to do that too. Because you need to, at some point, look at all the data and figure out what can happen. And here is the actual benefit. Okay, the benefit in this case is you see that the average of whatever in terms of the time it takes drops significantly in terms of and it's more regular. Right? Every time I talk about performance, it's really important to talk about two things. One is what is the P99 is, which is 99%. Average is not as good an estimator of the quality of the system, real-time system, as a P99. Probably 99% of the requests are under some value. So that's kind of how we talk about it. But if you look at the top, right, they were getting about 1.5% timeouts, or in terms of deployment. Once they switched over to our system, which is more predictable, they were able to reduce the timeouts to virtually nothing, 99.95 to 100%, pretty much. Which means, I didn't do the calculation here, but if you have, if you're doing like billions of dollars of transactions, if you're missing 1.5% of it, that is a lot of miss. Okay, like a million or more per day. It could be like, which means it's just risk. You don't know whether something was fraud, but you had to let it through. And that is not a great way to run the business, because now you've exposed yourself and you might have to claw it back, and there's a whole bunch of work. So if you could eliminate it, so you actually have a fraud score, which you believe in, before the thing goes out, that's actually really, really important. So there's a real business value here in terms of being predictable and being able to do it in real time. So this is the second use. This is the first use case we had. And this is basically what happened. SLA improvement was 30 times. 30 times they reduced in reduction in number of fraud transactions missed. Okay. While they reduced the servers from 360 to 20. So I talked about both of those, right? So because it's so predictable, we're able to keep your latencies very low. So you can actually complete your fraud score virtually 100% of the time. But then we can do it at a lot less cost because of the SSD pieces I talked about. Which means I can now put all my real-time data in SSD. I can compress the servers from, in this case, from 360 to 20. And that's game-changing, basically. Now, what it means is not like you've solved something, because now you can go 10x, and it's still affordable. It goes back to the point I was making about startups starting and growing big. We've seen a lot of that happen, and you don't have to worry about cost of infrastructure as much, because your business will just keep growing. On the second use case I mentioned in the beginning, how they benefited was very interesting. If you look at the results benefits part, first of all, they reduced the response time to 2/3 or whatever, what they got, which in itself is not that, it's good, but the more interesting thing is it's more predictable. As a result of which, they used to, so when somebody like ThreatMetrix sells a service to banks, they sell, hey, I can get you an answer in 100 milliseconds. And that means like, they only get paid if they get them an answer in 100 milliseconds every time the request comes. And that costs something per request, per completed request. And with once they switch to Aerospike at some point, because all these techniques I talked about, they could go back and say, hey, you know what? I can guarantee you a result in 50 minutes. If I do that, will you pay me 3 times the amount you're paying per request? And they got that through. So which means the quality cannot suffer, right? Because you still have to look at all the data, get it down in 50 milliseconds, then the customer will pay you more. And that's literally what happened. They also saved a bunch of money and they reduced the number of nodes from 450 to 30, but that's all on their side. From the business side, they were able to sell new offerings, which I think is fundamentally important. And all of this kind of impacts the work that we do, because if I'm definitely interested that my particular interactions with my bank are really efficient when I go there. And then if they can identify this better for everybody, and then they can keep the people out who are basically trying to spam the system and trying to break into it, if they can do that efficiently, then all of us have a better service, and the business is actually safe. And again, this is the same story. If you look at this curve, the latency curve, you see the latency in Aerospike is sub-millisecond, and the latency there was like 5 to 6 milliseconds. And this is for one request. But if you go and look at the actual application, it will not be this big a fall, because a database is only a portion of the request, but it's more predictable. As you can see, they got to 2/3 of what they have. This is what I mentioned earlier. So these are like real things that happened almost like 10 years ago in many cases. You can actually talk about it. This one is another one. This is the last use case I had about the brokerage firm with a bunch of positions and so on. So they were actually managing very few terabytes before and the number of objects. They were able to expand everything quite a bit. Okay, and I think the numbers right now are much more, which I can't share, are much higher than what they were. This is all like 5 to 6 year old data. But even there, you could see that they could run these risk calculations on their entire portfolio every few minutes. And now the portfolio is double to triple, and they're still doing it. So essentially, the way I would talk about it is to summarize, right? If you store and access more personalization data, the hyper-personalization that's going on, then you can use AI algorithms to make the best possible real-time decisions. Because every one of the things I talked about, I didn't go into the details of the algorithms, but they're all typically ML AI algorithms. They are not the latest AI, greatest Gen AI. It is not yet fully clear where the ROI for real time is in the new Gen AI areas, but we are working with many of our existing customers who use the traditional AI to figure that out. That's still work in progress. But the one thing we can be sure is it's going to come in fairly soon, because so many people are working on it, and I've seen a lot of evolution over the last 6 months. In fact, this is something we are also working really hard on. So to summarize, right, real-time decision making has very strict SLAs, typically tens to hundreds of milliseconds. You can't even wait for a couple of seconds. I mean, nobody waits on a website for 2 seconds. I mean, I've never seen it anybody anymore. Maybe like half a second is too much. Okay, 200 milliseconds is about, I think how long it takes. It's about the max, the outer bound. I think. So all this has to happen really fast, and it's actually good. And the other one is, if you access the more recent data has more value. The fact that I bought something like on the website right now, I don't know if it happens to you, but when you go somewhere, when you book a ticket or something, you start seeing a bunch of retargeted ads coming to you about it. Right? And typically they are at least like one trip behind, in my case. Which is not useful, because I'm not even going to look at it. Right? I've already gone, come back, and now they're showing me ads for Hawaii or whatever it is that you are in, right? So that's not going to work. So recent data is important, but then that's kind of the hard problem, because if you put data in, and this is where a lot of these databases for decision making have a problem is, can I ingest all the latest data and still make it available immediately? And that's kind of what this entire talk is about, right? We were able to ingest all the data fast, we're able to make it available immediately, so you can make better decisions. Be it fraud, be it recommendation, be it something else, doesn't matter, all these elements. So I think that's kind of what the next point is. And then you're going to have to work this at scale, because if you don't have people who are basically, you can't have like half the people get great service and half the people not get great service. Okay, everybody has to get great. It doesn't matter. And then sometimes you get spikes. And when you get spikes, that's where I think where something like Aerospike really helps. We have at least a couple of customers who get enormous spikes. And this is by design. One of them is a fantasy sports company. It's actually, I don't know if you know about cricket, if you know about cricket, but it's like in India, it's like people are mad about it. Okay? So the fantasy sports stuff, like Dream 11 is a company with a customer of ours. So every time a match happens, before the match happens, people are finalizing their teams. Okay? And that happens 2 minutes before the match starts. If you get access to every one of those requests, you can't actually continue to make money off of that particular event. And this happens, whenever you see something failing, when it's going at, when there's a huge spike, that's because they don't have many of the things that I talked about today. Basically, they can't deal with it. They didn't plan, they didn't have the right capacities, but also they don't have a system which can adapt. And that is really hard to do, because if something fails in the middle of that, the system still has to deliver that. Because that is, and all the techniques I've talked about here are used to handle those spikes. The distribution stuff, the whole data center goes away, it works. In case a machine goes away, it works. There's enough capacity in it to do both data rebalancing as well as transactions, and you don't lose data because it's got strong consistency. All of the things I talked about come together to solve a problem like that. Okay, I think I have an example here, but basically it's like, you have people who are trying to access something, and then you have to determine if somebody is actually fraud or not. So and how much data do you have to store for that? Do a good job. In this case, the day 8, that's probably a fraud. But the point is, to detect it, how much data can you store? If you can store more data, but then you have to be able to access it in a short amount of time. Because if you can't tell within the short period of time that the fraud is happening, that's not useful either. So again, a system which can process more data in a short amount of time to make the best possible decision is actually something which can be applied over and over again. And fraud is actually an interesting example, because the fraudsters are also advancing. It doesn't stand still. Whatever was fraud 2 years ago is like, nobody does that. They do something new and more advanced. So which means you got to keep up with it. There's a whole arms race going on. So I will conclude with that. I think that must be the last slide. Some QR codes you want to take a look at.
If anyone has questions, we do have a microphone here. If you wouldn't mind talking to the microphone. Thank you. We might have to turn. Thank you. Turn it on. Is it on?
I think so.
Yeah, there you go.
Okay. So great talk, by the way. So one question I had was, two pretty long thoughts that managing data that's async, like async being access. Have you tried any frameworks where the model itself needs to be asynchronously updated? So, for example, if we're training a learning model.
Yeah, that's actually a great question. We are not usually in the loop for model training, because what we have seen is data that is coming into Aerospike is shipped asynchronously into another system. So we have all these connectors through which you can ship we have what's called change data capture, and you can ship them to somewhere else where they can do the model training. And we've seen that happen a lot. Not too much of model training happens natively on the Aerospike database. But we are in the ecosystem of it. That's the way you look at it.
wanted to ask, so your architecture runs on SSDs primarily, but what is the wear and tear of like regular SSDs? Because you could couple with like startups, but they don't have enterprise grade SSDs. So I wonder like what kind of testing have you done to like ensure, okay, like this is still high throughput, high writes, like it's good, it's fine.
That's actually a great question because we started the company, what, 15 years ago? So the SSDs then were really bad. I think can you hear me? The SSDs were really bad. But our algorithms take care of it. I didn't go into the details of it, but wear leveling is a serious problem. Does everybody know what wear leveling is in SSDs? Okay, I see a lot of people saying no. I'll just try to explain in a sentence. What that means is you can't write to the same location in an SSD more than some number of times before that thing will basically fail. That's fundamentally the simplest way to put it, right? Is that fair? Okay, so because of that, because of wear leveling issues, our algorithm from the beginning has been named because has been based on copy on write. So we don't actually do in-place writing of data to SSD at all. We've never done that. So even with those really poor SSDs, we had a limit on the transactions per second that we could do on it. But we could have more SSDs and we could achieve it. And as SSDs started getting better and better and better, we got NVMe, and now we have like Nitro SSDs in Amazon, and they're like really better SSDs on Z3s of Google. Those were actually developed. Google's product teams and Amazon's product teams collaborated with us to develop the i4Is and the Z3s. But fundamentally, the SSD technology has become much better. So even with the bad SSDs before, we didn't have this issue as much. But what we will do, and this has happened, as our cloud partners tell us, is our customers have used some of those bad SSDs and burned them down in the data center because of the way we run it. But then if you're running on the cloud, you burn down the SSDs, the cloud provider has to provide you with other ones. So what they did was they ended up building better systems. So it's actually good feedback.
I have two follow-up questions to that. So how much of it is like, because your system's agnostic to like cloud providers.
Yes.
So how much of that is like the algorithm being written for different like enterprise grade SSDs, or is it completely always agnostic? Is it like a continuous integration process of like whatever the infrastructure looks like?
The good news is, right, for SSDs, okay, the question is how dependent are our algorithms on specific enterprise SSD advances? We have been from day one involved in working with the people who built firmware for SSDs, including Intel, Samsung, Micron, all those in the old days. And these days, it's really the cloud providers. So we work closely with Amazon and AWS. We have a team in our group who actually validates these SSDs for performance before they get released into the world. So we have a feedback loop that we provide for them. That's how it works. We don't do any work on it. We just simply test them. Give them we actually wrote what is called a basic tool, which will take an SSD and it will run on it and give you stats on how well it performs. And then we can share it with people. And people can run it themselves. Good questions. Any more?
Are you able to go? Okay. Excellent. Well, thank you so much.
Thank you.
He has agreed to stick around if there are any individuals that have additional questions that they did not want to share publicly. So thank you so much for coming, everyone, and we look forward to seeing you next academic year.
Yeah, next year. Let's go. Woo!